morning. I do have to put the ones from yesterday up, so I'll have to remember to do that too. I'll probably do that right after class. It takes a while for them to process, so we'll see how long that takes. We had Zoom on Tuesday, right? That was yesterday, right? Yeah, we were here. I don't, as I said, I don't have the video for that up yet, but right after class, I'll post that. It takes a little while to process because it has to translate from the system from Zoom into an MP4, and then when I upload that MP4 onto YouTube, it has to process again, go through its filters. So it might take a while, but right after class, I'll start that process of uploading those as well.
So you're now on YouTube?
Oh yes, I'm a star. I have 19 followers.
I know there's other people like I have 100,000, or I mean, if your videos are simpler enough that people understand, you'll get a lot of people coming on.
I'm proud of my 19.
Just kidding, man. You're doing all fine, man. You're awesome.
So let's look at these. So the sign of, so we talked about, using this tool yesterday. You might notice I have changed the format a bit. I'm using a different tool for the whiteboard-like thing, and it's going to allow me to edit things a little different and input things a little bit differently. So hopefully we'll take advantage of that. But if anything's weird, let me know, just because it is a new system again. Yeah, I thought Nick, thanks for mentioning that calendar. I did try to go in and fix the Tuesday days on that calendar. I thought it updated. When I went back and looked at it again, it had the Tuesdays on. But if it's still not showing those, yeah, I'm not sure. I'll go back and try to fix it again. The links are universal, so you don't have to click on the particular link for a particular day. But our schedule is Monday, Tuesday, Wednesday, and Thursday. So we will be here Tuesdays. I don't know why that calendar is being persnickety, but I'll try to figure that out if it's still being weird. But I do thank you, Nick, for having brought that up before, so I can at least know that that's being weird. It's fun to learn new things, isn't it? I'm going to go with yes, because that's why we're all here, right? So we talked about using this tool and being able to build this tool. This is a good tool to have, just kind of constant access to, have this kind of at your side as we do all this stuff. So that sine of 7 pi over 4, we go down to 7 pi over 4. The sine is the y values, so that y value of negative square root of 2 over 2. I do have to remember that you can't see the cursor on this tool, so I have to actually, why isn't that working? Draw stuff. Oh, that's why it's not working. So we've got to go down to the 7 pi over 4. Here's a new tool. Down to the 7 pi over 4 down here. Grab the y value, because that y value is our sine value, the negative square root of 2 over 2. So the sine of 7 pi over 4, negative square root of 2 over 2. Cosine at 3 pi over 2, so we're going to go around here to 3 pi over 2. Cosine is the x value, so cosine of 3 pi over 2, 0. The tangents are always a little bit weirder. Some of you on the forums were talking about those square root of 3 over 3 and the 1 over square root of 3 problems. Those are usually tangent issues. So if we look at that tangent of 7 pi over 6, 7 pi over 6 is down here. So the tangent is going to be the y over the x. So the y value of 1/2 over the x value of negative square root of 3 over 2, they're both negative. We could, that technically is the tangent done, but you certainly wouldn't leave it like that. It's ugly. So we're going to clean that up. I'm going to multiply top and bottom of that by 2 and cancel out those negatives. That's going to give us 1 over the square root of 3. We, of course, don't like the irrational value, so I'm going to rationalize it and get that square root of 3 over 3 that you guys were talking about. Yeah, usually that's a tangent result because the halves cancel. Questions about any of those before we go on to some of the new stuff? Hopefully these things are getting more comfortable. A lot of you guys were saying you really liked this tool, and that's great. It's a good tool. Okay. So what we wanted to keep looking at today was graphing. So let me grab myself some axes. That's one of the cool tools I now have. Quickly make axes. Ooh, I didn't want that to go away. Let me try that again. So we talked yesterday about trying to graph sine. So we're going to be graphing y equals the sine of x. And you'll either remember from yesterday or be able to go look at that from yesterday. One period of the sine function goes between 0 and 2 pi, because as we go around from 0 to 2 pi, we go through all of the values for sine. And then it starts to repeat itself again as we get to those coterminals. And since the sine is our y values go up to our positive 1, and then back down to 0, then down to -1, back up to 0 as our y values go around that circle. So we went up, waved down, ending at 2 pi. It's a good trick. If ever you miss your dots, just make them bigger. So that was our graph of one period of sine. Went up to a maximum of 1, a minimum of -1, and went through its whole oscillation in 2 pi radians. It's going to hit this halfway point at pi radians. It's going to hit that max at pi over 2 radians, and that minimum at the 3 pi over 2 radians. So that's where we were yesterday when we stopped. What I want to talk about today is manipulating this and modifying this. Now, hopefully, you remember your tools from Math 111, and you remember some of those function translation rules. Remember when we raised and shifted and stretched and compressed functions in section 3.5 of Math 111? So let's say we take our function sine x. I'm going to use those parentheses to help emphasize where our modifications are. So our sine x, and we want to say add 4 out there. I want to look at how is that going to affect this graph. Of course, this graph does continue as we talked about yesterday. I'm just graphing a single period of it. So you might remember from your function translation in Math 111 that if we added or subtracted a value outside the function, we were essentially taking those y values and adding or subtracting that amount to them. So what's this going to do to that graph? It's going to take it and lift it up 4 units. So it's going to, instead of starting at 0 and going up to a max of 1, this one's going to start at 4, go up to 5, down to 3, as it goes through that same oscillation. Up to my ability to effectively draw it. And again, then continue from there and continue from there. So say we have something that instead of oscillating between a +1 and a -1, we want it oscillating between a +3 and a +5. Okay, that lift will make that equilibrium point, as it's called. That equilibrium point will move up to 4 instead of 0, and we'll have the graph take place there. Well, that's just the beginning, right? We have lots of different modifications we can do. Let's stick with the output values. So let's say this was y equals instead 3 sine x. Again, you might remember what happened when we multiplied on the outside when we did translations. When we multiplied on the outside when doing translations, it was a stretching. Oops. Go away. So what's going to happen? That as we put in our values between 0 and pi and 2 pi and so on, it's going to go 3 pi and so on, negative pi, negative 2 pi, oops, and so on. As we go through those values, the sine is going to output values between 1 and -1 still, but then they're going to be multiplied by 3. So each one of those values is going to increase to 3 times the value it was before. So it's going to stretch the graph out. And importantly for us, it's going to change what we call the amplitude of the function, how high and how low it goes. So instead of going up 1 and down 1, it's going to go 3 times that. It's going to go up 1, 2, 3 units and down 1, 2, 3 units. Now we use the term amplitude for a wave, but we often think of amplitude in terms of sound and loudness. And this really is the same. When we increase the height of that wave, we increase the loudness of the sound if this was a sound. So, comparing this to sound waves or light waves is quite reasonable for us. So the language, it's one of the reasons the language is going to stay consistent. So it's going to end up being exactly the same shape, just stretched out because it has that higher amplitude. So that would be one period, and then it would continue again in both directions. Oh, that one got squishy, sorry. Hard to go that direction for some reason. So that one period is still the part here. Same shape, just stretched out by that higher amplitude. So these two translations tend to be the nice ones outside. Anytime something's happening outside the function, it tends to be a very direct translation. And we can put them together. So say somebody asks us to graph y equals, say, 3 sine of x minus 1. If we want to graph that, I wonder if I can push that over that way. No, I can't. So if we want to graph that, we haven't done anything to change our inputs. Nothing's happening inside that function. So it's still going to be 0 pi, 2 pi, negative pi, negative 2 pi. So it's still going to be on the same, one period from 0 to 2 pi. But this -1 is going to change our equilibrium point or equilibrium line to being down here at -1. So that's going to become the center of our oscillation because of that -1. And that 3 is going to cause us to go to an amplitude of 3. So from that center line, we're going to go up 3 and down 3. So 1, 2, 3 at 2, and down 3, 1, 2, 3 to -4. So our graph, our wave, is going to fit in between those two boundaries, centered at that equilibrium point. It's going to reach its halfway point by the time we get to pi. It's going to reach its end by the time we get to 2 pi. Its max at a quarter of the way through. Its minimum at 3/4 of the way through. And it's going to fit nicely. Yeah. Fit nicely in there. Yeah. Just again, make the dots bigger. And then, of course, continue on with the same pattern and period. Questions about that?
Yes, I have a question. Can you hear me?
Yep, I can hear you.
Okay, so I noticed that 3, I didn't really stop to think about it until now, just a flash of thought. So that -1 and that 2 equal that 3 in the front of sine?
Yes.
I'm just thinking if
that -1 is our center. So we're taking that -1 and going plus or minus 3. Yep.
Wow. Okay. Okay. So that means that -1 would plus 3 would be negative. Oh, okay.
Yep. The -1 plus 3 would be 2. The -1 minus 3, that -4. Yep.
Oh, okay. Oh, wow. Okay. I wasn't thinking it like way before. Oh. So the middle is the midline. You say that I know we went over this. It feels like I did this in 111, but the
Yeah, you'll have done
-1.
similar things with 111. Yeah.
Yeah. So what the -1 is the midline, and the top 2 and the bottom. It's that. Would that be the amplitude?
Yep. That
So
3
that would be.
we call the amplitude. It's how far is the wave going to be displaced from its center, from its equilibrium. So this thing is being displaced 3 units in both directions, up and down.
So let's say that line was above the the x-axis, and
This
it
one?
was yeah. So I mean, it's 3 up, 3 down.
So just as an example, if we had 3 sine x, say plus 2. Oof, that's terrible. I don't know why I'm still using the weird thing. So where would our center line be?
Would it be in the middle?
It would be in the
Of the
middle
line?
at that 2. So at +2, that would be where our new center is. Instead of being centered about the x-axis, instead of being, our normal sine curve is centered around that x-axis. This lift is moving this thing up by 2 units. So it's going to be centered now around 2. And it's going to go up 3 and down 3. So from there, up 3 is going to be 5, and down 3 is going to be what?
It means it's gonna end up on 5.
Well, 5 when we go up. How about when we go down?
A negative. Wait. Okay. Let's see. That would be another 5, but that would be like reduced, I think.
Well, it's still only going 3 units from the center. So from 2, it's going to be 1, 2, 3. So it's going to be down at
Okay.
-1. So that would put our wave in between that as a max, that as a min.
Okay, I'm kind of lost too. The period is
Well, we
the
haven't talked
length
about
from.
period yet.
Okay,
Much.
okay.
Other than
Sorry.
that, the basic period is a 2 pi. That means this whole oscillation, the one oscillation is going to happen between 0 and 2 pi because that's our base period. In a very short time here, we'll start messing with that period. But for right now, that's our period. So let me have you guys try this, make sure we're happy. I'm going to throw kind of a wrench in this for the fun of it because it's good to amuse myself, right? Let's say -5 sine of x. Oh, I don't want to go up or down. Let's go up. +2. So sketch that graph over one period. Do try to decide if you can remember what to do with that negative. Cool. You don't have to draw these kind of dotted lines in here. I really like them. I think they give me a nice reference. So one of the things I'm going to recommend as we go along with these, whenever you're trying to graph one of these things, writing out the amplitude. We're going to talk about period and phase shift next, but writing out what the amplitude, period, phase shift, and lift are is really helpful. That way, if you're still struggling with your graphing and your graph looks kind of ugly and weird, you can show me, or I can see on your scratch paper when we do tests, that you had the right amplitude, period, phase shift, and lift. So you can get points for that, even if your graph ends up looking like something it shouldn't. So it's a good habit to write out. So that lift is, you could call this a vertical shift in translations. It's often referred to as a vertical shift. I think your book calls it a vertical shift a lot. Lift is kind of a casual term for it. that lift would just be that nice positive 2. If this lift was a negative lift, if it was going down, we still often call it a lift. It's just a negative lift. It's going down. Our amplitude. What should, type in the chat over there, what should this amplitude be? Good, Shay and Nick, both of you. That amplitude is technically the amount of displacement from center. So that negative is certainly going to tell us what direction we go, but the amplitude, the amount of displacement, is the absolute value of that -5. The amplitude is 5. For our strict amplitude, it doesn't matter which way we're going, it matters how far we go. So the amplitude, the loudness of this sound, it doesn't matter whether it starts going downward or starts going upward. The loudness is proportional to that positive, to the amount of displacement. It's proportional to that 5. So do be careful about that when asked the formal amplitude. Yep, just that positive 5. Now our natural period so far is 2 pi. We haven't adjusted that. The capital T is commonly used this as a symbol for period. I'm not sure why. I sometimes like to say it's from the Latin, but I have no idea. But so we often use that capital T for period. If you think in terms of sound and frequency, that period is actually the reciprocal of the frequency. So whether you're used to talking in terms of wavelength or talking about in terms of frequency, whichever one you're used to, you can switch back and forth just by taking the reciprocal. This is our wavelength. It is our period. It could be time, Felix. Yeah. Capital T for time would be weird, but it would stop it from looking like a variable. So maybe. So we're going to go from our starting point at 0 out to our 1 period in 2 pi units. So we're going to be at that equilibrium point at the beginning. We're going to be at that equilibrium point at the end, because remember, our basic sine function starts at that equilibrium, waves, and then ends at that equilibrium. The big issue is what this negative does is instead of having it start by going positively, that sine is going to output positive values, and that negative is going to make them negative, make them be subtractions. So instead of having that that sine function start by going upward, it's going to start by going downward. So it's going to have its minimum there at the pi over 2, going to get back to our equilibrium at pi, and then at 3 pi over 2, it's going to be the maximum instead. So it is going to be that vertical reflection, that vertical flipping that negatives often cause. And again, it will continue. Questions about those? So if we want to think of it in terms of circles, that basic circle that we're looking at is a radius of 1. So the sine displaces how far up and how far down we're going. So that amplitude change is really the radius of that circle. So as we change this from a 1 to a 5, we're making a bigger circle, a larger amplitude of that wave. That 2 really is moving that circle, if you want to think of it still in terms of a circle, is moving that circle up from the measure of a zero, having it occur, kind of upward in space. As we go to period shifts are having that's the rotating around that circle happening faster. So it's all about the length, position, and speed of that rotation if you want to think of it in terms of a circle. But we actually don't have to. These can be lots of different things. Lots of different things are measured in these sinusoidal graphs. For example, if we look at, your book likes examples like hours of daylight. If you start in the spring, if you start in the fall, the hours of daylight goes down to a minimum for the year, and then back to the, a 12-hour day, and then the time of day goes up over the summer and then back down. That's not necessarily measuring a circle. You could argue that those orbits are circular and so forth, and that's a good argument. But that oscillation from low value to high value, back to low value to high value, it doesn't have to be locked into a circle. But if we wanted to reconnect it to a circle, radius and speed of rotation, if that helps, Felix. Let me know if that helps. Or is it just for graphing? Yeah, it does have corollaries. The vocabulary that we use, period, phase shift, amplitude, is more based on electronics and sound than it is on a geometry. But we could translate it if we wanted to. Sure. Okay. So we do want to start talking about messing with that period, because we're going to mess with that period a lot. Right now, our graphs have always had that, zero goes through its oscillation, stops at 2 pi, halfway through at pi, at a max or a min at pi over 2, and so on. And before we talk about period, I do want to make sure we're aware of something, or keeping something important in mind, and that's that this scale is, the fact that it's written in terms of pi often throws people off, and people forget what it is that they're looking at here. Remember 3.14, pi is the value 3.14159265358972. Goes on forever. But that means right in front of that is the number 3. Pi over 2 is about 1.57. So there's our 1, there's our 2, our 3, our 4, our 5, our 6, 7, 8, 9, 10. So one of the reasons graphing in radians is so nice, particularly when you graph on things like your calculator, is that one oscillation really does live in that nice little spot between 0 and 10 with some space to spare. So I don't really want you to think of this axis, because it's in terms of radians, in terms of all these pi's, to be any different than the x value or x axis that we're used to. It's just we're highlighting different tick marks because those are the tick marks that are useful for us. Fair? And a lot of times when you graph, one of the things that'll happen sometimes, you'll ask your calculator to graph like one of the sine functions or cosine functions, and all you'll see is this big straight line. And it's in your normal 10, negative 10, 10, negative 10 window. And people will say, their calculator's being funny, or they don't get why their graph is right or wrong. But usually this happens because somebody's calculator is in degrees instead of radians. So what the calculator would want to show you is that oscillation going between 0 and 360 degrees, but you're only giving it from 0 to 10 degrees. So from 0 to 10 degrees, it looks a lot like a very straight line. Does that make sense? So if you're ever getting a weird output like that in your graphs, make sure you look at, hey, am I in degrees or radians? And that's one of the reasons we tend to like to graph in radians. We'll talk about a couple others as we go along, but that's one of them. So keep that in mind, that all those numbers are in there. Oops, went too far. But I'd really like to be able to have my oscillation, instead of going between 0 and 2 pi, I'd really like to be able to make it shorter or longer, or instead of going from 0 to 2 pi, have it go from, say, 0 to 12, because I'm trying to measure over a 12-hour period, or from 0 to 8 if I'm trying to measure like tides or something. So I'd really like to be able to control how fast that oscillation is. And nice thing is we can do that. And we've seen how to do that in some of that 111 material, depending on how much you remember that. But we can compress our graph, thus change its period, by multiplying that value on the inside. So if we look at this sine 3x, what that's going to do is it's going to take our oscillation and speed it up by 3 times. So our x values, like if we tried to go from an x value from 0 to 2 pi, as the x goes from 0 to 2 pi, this whole value, that input, is going to go from 0 to 6 pi. So it's going to happen much, much faster. So what's that going to do to our period? Well, it's going to take our base period of 2 pi and divide that base period by 3, shrinking this thing's period. So instead of going through one oscillation from 0 to 2 pi, this is going to go through one oscillation from 0 to 2 pi over 3. And that's where one oscillation is going to sit. So it's going to happen much, much, much faster. If we tried to draw it in that other scale out to 2 pi, instead of going through one oscillation from 0 to 2 pi, it's going to go through 3. 1, 2, 3. It's going to happen. I don't know why I dotted that second one. It's going to happen faster. I'm rescaling this so we can look at it. The halfway point is going to be half of that, and half of 2 pi over 3 is just pi over 3, so that's going to be the halfway point. That quarter point is going to be half of that's pi over 6. And 1 pi over 6, 2 pi over 6, 3 pi over 6. So that 3/4 points is going to be 3 pi over 6, which would reduce to pi over 2. So those are going to be the equilibrium points and the min and max points. We often want these 5 points. They're often referred to as our quarter points because they break us into 1, 2, or 1, 2, 3, 4 different sections. But once we have that period adjusted for, we're still going to go up to a max of 1 and a min of -1. And it's going to behave in the same way. Max out at that first one, equilibrium at the second one, then minimum, back to equilibrium. So just on a shorter period than it was before. Questions about that? Seeing some no's. So let's try making this a little more fun. Let's say y equals the sine of pi over 4x. Now Now our amplitude is still 1 because there's a 1 right there. We don't have a lift, so our lift is 0. But I want you to compute what this new period would become. Should we type it or just find it? Do wait a minute or so, make sure everybody gets a chance to play with it a little bit, and then go ahead and type it. See if you guys can argue with each other. I always love when you guys argue. But yeah, in general, when I ask those things, if you know it like right away, do let people play with it for a minute, because oftentimes when an answer pops up, everybody else will just stop. So I don't want that to happen. But after a minute or so from when we start, throw it up. So if you've got a value, go ahead and throw it up. We lost Nick Varner. Where'd he go? Garrett, the frequency would be 1/3. The frequency is that 3, the period would be is 2 pi over 3. The frequency would be its reciprocal, 3 over 2 pi. Oh, you are here, Nick. Oh, you're just off my screen thing. Okay. Good. So the period here, we're going to find the period the same way. And this is really going to be a general formula for period. Anytime we have a period that we're going to be modifying, we take the basic period. Our base period for sine is 2 pi, and divide it by this b term, divide it by the coefficient of the x. So we're going to divide that by pi over 4. Now that pi over 4 might look mean, but if we multiply those, turn that division into multiply, or however you want to handle the division, notice it makes those pi's cancel. So that gives us a period here of 8. We don't have any phase shift yet. We'll talk about those definitely tomorrow. So our phase shift is nothing. That's what happens when we add things on the inside here. So we'll talk about that tomorrow. But this period of 8 is going to make this hopefully quite handy. As I said, a lot of things don't oscillate in multiples of pi. If you've got something that's fluctuating over 8 days or 8 hours or 8 minutes or 8 whatevers, being able to have that oscillation model, that period properly, is important, is helpful. And we can do that just by making this coefficient whatever's necessary to make this equal whatever period we want. So now this thing's going to oscillate, go through a full oscillation between 0 and 8. Again, when we do the phase shift, we'll move this move this 0 off that center location, but it's going to go through that full oscillation between 0 and 8. So that halfway point will be after 4, let's say hours, and then that max at 2, that minimum at 6. So we can really have that frequency become anything we want: rational, irrational, nasty fractions, nasty decimals, nice numbers, anything we want. Just by controlling that b, we can control the period. just like controlling that A will control our amplitude, that D will control our equilibrium, and tomorrow we'll talk about that C, which will control when we start and stop. All right. Before I let you go, I want to mention, I'll probably move back the section on inverses. I don't remember, I think it's due next Monday, but I want to spend a little bit more time talking about that. And I don't want to rush the section on graphing. There's a lot of important stuff here on graphing, particularly once we get to solving. Being good with these skills of what these different numbers are doing is real helpful when we talk about solving in our next chapter. But one thing I want you to keep in mind, we've been spending a lot of time today, and we'll keep spending time tomorrow talking about graphing sine specifically. We do have 6 trig functions we have to graph, but all of this stuff we're learning for graphing sine will translate very nicely over to graphing cosine. So once we're good at graphing sine, changing to graphing cosine is one step. Once we can do those, changing to graphing secant and cosecant is one step. Learning to graph tangent, once we have these tools down, there's a little bit of an adjustment for tangent, nothing huge. But so all of these skills build on each other very nicely. So once we've mastered sine, doing all the others is going to be really easy, ideally. Tangent is a little bit squirrely sometimes, but the other ones are nice. And if you're curious, cotangent, we never graph cotangent because cotangent sucks. So don't worry about cotangent. And it's also, frankly, not that hard once you can do the other changes. So yes, we're focusing a lot on sine. Don't worry about thinking like, oh my gosh, we're going to have to do all this work for all 6. No, all of this work will translate to all 6 very, very nicely. So don't let that panic you yet. Okay, questions about any of that? Do go play with your graphing. And if anything comes up that you need, let me know. I got 1/8 as the frequency. Yep, Felix, if you're looking at the frequency of this wave, the frequency would be 1/8. The period is 8. The difference between period and frequency, period is like if this was time, period is 8 seconds per oscillation, where frequency is 1/8 oscillation per second. So it's which one you're doing. If you're trying to do seconds per oscillation, or that's a wavelength argument, we talk about period. If you want to talk about frequency, oscillations per second, for a pitch, it's just the reverse. So that's that relationship between period and frequency. Did I spell frequency with a C? Frequency. Yeah. Felix, does that make sense? Cool. Okay, anything else? I do try to get you guys out of here on time. Nick, we're doing good? All right. Sam, say hi to your brother. Okay, have a wonderful day. I'll see you guys tomorrow. You're very welcome. Did all that go okay today, Dominic? Yeah, good. Just rush off. I hope they all have fun. 1 hour and 10 minutes.